We will now study a larger case study. The case study is fluid simulation, and we will use a partial differential equation for doing this simulation. So we need to write down this partial differential equation. So let me just give you how that looks like. It's gonna be the incompressible, Inviscid, Navier Stokes equations that we are gonna solve. And now for some fancy math explaining how that looks like. We need a velocity field, a vector field u. We need the time derivative of that velocity field. This will be the acceleration. And we need to have some advection term, basically describing how the fluid will push itself around. So just need to write down all the latex code for making a nice layout of this. This is the advection term. And then of course we also need some pressure forces. The pressure force is going to make sure that the fluid is incompressible. That means that there are no volume changes. I cheat a little bit here in this equation because I left out the density field. So this is how the equation looks like. We can just drag it over here. You can see it's right here. Okay, so this here, that's the acceleration term, advection term, and pressure forces. We also need an extra condition. You can see here that this is a two-dimensional. We're going to work in two dimensions, so this will be a two-dimensional vector field. And this pressure field is a scalar field, so we have three unknowns to solve for. But this equation, this vector equation, only gives us two equations. We need a third equation to make sure we have a well-posed model. And the extra condition we're going to make is basically making sure that the fluid has a zero divergence, meaning that the divergence of the fluid is zero, like this. It basically means that if we have a little cell, an arbitrary cell volume, whatever goes into that volume must also come out of that volume. So this combined is the equations we are solving. The full Navier-Stokes equation would have some extra terms. It would have a viscosity term, and there would probably also be some external forces accounting for different sort of things. But this is the basic partial differential equations we're going to solve. So from a computer science viewpoint, we immediately see that we somehow need to deal with storing the variables for the velocity field and pressure field. So we need an x component of velocity field and a scalar for the pressure field. We can write that up too. So we have the x component of velocity field. We will use the variable name u for that. So notice that one is with a bar above, that's the velocity vector, and just the scalar x component field is just u. And the y component we will call v. And this is of course two-dimensional velocity field like this. And the pressure field, simply just a scalar field like this. Okay, Then we're gonna use a grid data structure to store our fields. So we're gonna create a grid. So now I've drawn the grid where I want to store the pressure field values, and I made it bluish such that we can see the locations, the grid nodes where pressure values are stored. This grid has 1, 2, 3, 4, 5, 6, 7 values along the x-axis and 7 values along the y-axis. I'm gonna use some symbols to remember these dimensions. So the number of grid nodes along the x-axis, or we will write that down as m. So we'll say m equal to 7. And the number of grid nodes along the y-axis we will call n, and that is also equal to 7 right here. We also need some more extra information for this grid. We need to know where it's placed spatially. I mean, what is the xy coordinate of this node in the world? So we're gonna need to know at least where one of these nodes are located. And we're gonna pick the lower left node, and then we're gonna remember the x coordinate and y coordinates of this node. So since this is sort of like the origin, we will call this O x origin x coordinate equal to, and let's just place this in 0.0. And similar for the y coordinate, I will need something like that. This means that if I want to know the x location of this node, I simply just count its index. So this would be index 0, 1, 2, 3, 0, 1, 2, 3. This is 3 by 3. So if I know the distance between two nodes, I would say OX coordinate, OY coordinate plus 3 times 3 times the distance between the nodes. I also need the distance between nodes. So distance along nodes in x direction, I call that dx, delta x. And since we want to make sure that we have small distance between our nodes due to Taylor approximations, I'm gonna say this is simply just gonna be, let's say, 1 divided by m. Similar for the y direction. I could have picked any values here. This is just to make it simple and easy. Okay, so this is the information I need to work with the grid nodes. And the equation to find out where grid node I, j would be placed would simply be OX plus I, the I index of a node, times the x, and the y coordinate would be like this, j, the j index of a node, times the distance along the y direction between nodes. So xi, the I coordinate, and the I coordinate of the, sorry, so this is for the pressure field. We have two other fields also. We have the x component velocity field and y component of velocity field. So we need to explain how these fields are located too. Okay, so we'll start out with the x component of the velocity field, and we will draw a new grid for that. So now I have finished drawing the U field grid, and the funny thing here is that it's actually not gonna be right on top of the pressure field, but it's gonna be displaced a little bit like this. So this is termed a staggered grid or a MAC grid. So notice now that if you have a pressure field value, I have actually a x component velocity field both on the left and right hand side. So this is very common to use this. And you might wonder why this makes sense, and I can just briefly show you by going back to equations we're going to work with. So at some point we're going to solve for a pressure field coming from this equation, where we're basically going to substitute that into the equation below to get a Poisson equation, which means that we have some differences of pressure values on the left hand side and a divergence field that will be moved to the right hand side. So it means that when we solve for pressure value, we're gonna look at a difference of velocity values. So it makes sense to solve for a pressure value and then having the difference of velocity values on each side of the pressure node. It will become convenient later on. Okay, so if we just compare the pressure field grid to the X component velocity field, we notice that for the U field we had an extra cell along the x-axis, but the same number of cells along the y-axis. The origin of this field is actually displaced from the pressure field by a half cell in the negative direction of the x-axis. So that means that we should subtract a little bit from the origin. When we do the implementation, we're going to cheat a little bit. We're not going to store origins for each grid individually. We're just going to store for pressure field value, and then if we remember what type of values is stored in a grid, we can make the displacement on the fly. So that means also here I would need to adjust my formula. Okay, we also need the y component for velocity field. So I'll now draw the v field grid also on top of the other three grids. I've now drawn the y component of velocity field and I made it green so we can see the difference from the two other fields that we are having in our simulation. So now I'll move the y component into its right place, and it should be located roughly here. So we notice again it's a staggered configuration in the y direction, and we can see that the number of grid nodes along the x-axis is the same as the pressure field, but we have one more grid node along the y direction, and the origin is this time displayed in the I direction and not in the x direction. So we need to make some small changes like this here, and for finding the grid node location we also need to make some modifications. It's not the x origin that needs to be modified, but the y origin coordinate that needs to be modified like this. So now we have the three grids in place. We know how to locate grid locations, and we know what extra information we need to describe the physical, the spatial layout of a grid. So now we are ready for implementing this in Mabel. So let me see if I can find my Mabel. Here it is, and we are ready. So a good idea is always to do a restart in Mabel, so we sure we have a clean environment. That will be helpful when we rerun this Mabel worksheet. So we need some to describe the number of grid nodes in the pressure field. Now I'm just gonna pick something. It's not really important what the numbers are here, and we're gonna have the origin also defined. I'm just using global variables for doing this. In a real application, one would probably wrap all this up into some nice data structure. But for this learning study case, we can just use global variables to work with things. That would be more convenient for us. And actually I don't want to have all this output from Mabel, so I'm just gonna replace semicolon with colon. And probably also a good idea just to write down a bit of comments so we can remember what each variable is about. Okay, this is the basic variables that we need in order to find locations in the grid. We also need some arrays to store the actual grid values. So we will have pressure field. I'm going to use the inbuilt Maple data structure called array. And this has to start with index 1 and it has to go to M and for the y direction like this. And we also need, oops, a little bit too fast. I'm gonna do it like this. And we need the x component velocity field. And we need to remember this has an extra grid node along the x direction. And the y component of velocity field, we need that one too. And this one has an extra node along the y direction. Okay, that's it. That's the basic data structures we need. Then we also need to create some procedures that can compute the xy coordinates of a given node index. So let's try and write that code. So we could call that get cell position, for instance. And it's a procedure and it takes a y and j index as input. And when we work with the math, we are probably going to use zero-indexed indexing, whereas the array data structure may use one-based indexing. So just to help me remember when I use one-based or zero-based indexing, I'm going to add a 0 to these indices. So I remember that this is zero-based indexing and not one-based indexing. That will make it more helpful for me to remember what is what. Okay, so let's see what this is gonna do. We're gonna compute some position, and let's use the vector data structure from the linear algebra package in Maple. So we're gonna create a vector with an x and y coordinate. And the x coordinates is gonna be the origin of the x component of the pressure field plus the zero index of the x node and the spacing, and similar for the y direction. This is pretty simple stuff. Okay. So scoping would make sure that the OX and DX get pulled in from the global scope. So we here need to make sure we have the local thing. That's just gonna be this one. And we're gonna return this vector as the end result. And just to make it explicit what we're doing here, we can pull in or tell Maple what global variables we're using like this. That should be sufficient. Let's see if I did right. Oh, sorry, something wrong here. It's a missing semicolon. Okay, let's see that worked out now. So this was for the pressure field. We need a similar function for the velocity fields x and y components. So let's create those. Get cell position of u, we can call it like this, and we remember that the difference is more or less only to have a small displacement here. And for the y component, it's pretty similar, like this, and the correction needs to be on the y coordinate instead. Let's see if this works out. Okay, that looks good. So far, so good. We now have the basic data structures in place and some very basic functionality for computing the x and y coordinates of some specified grid nodes, but it's quite not sufficient to do fluid simulation. We need some more basic data functionality in our data structures. So let's go back and look at what is needed. So when we're going to work with simulation, we are in some cases going to need to look at a arbitrary position somewhere in the grid and trying to figure out what is the pressure value or what is the velocity at that specified position. And the position might not be co-located with the actual grid node of the underlying grid. So we need to be able to somehow interpolate information to any location in the world from these grids. So we're going to talk a little bit about how to interpolate values. And we're going to make this discussion a little bit generic, so I'm just going to say from a grid. I don't know if it's going to be the U, V, or P grid that I'm working on, and actually I don't care. I'm just going to say I'm going to have a location and I want to interpolate a value from that grid at that specified location. So the basic idea here is that if I'm going to have some position, so we can just take the grids here, or take one grid out. Let's just work with the pressure grid as an example. See if I can catch it, or we can just take it up here. Gonna copy this. Okay, so now we have a grid and we need a location where we want to know what is the pressure value of that location. Let's say we're gonna use a purple star to indicate that location. There you go. Let's make it a little bit bigger. Somewhere here, let's say right here, we want to know what is the pressure value at this star location. Okay, so the way this works is that we first are gonna get a local vector with respect to the coordinate frame where the grid is defined. So we're gonna create a vector. Just make a nice color for that vector. Let's make it like this. Okay, the vector is going from the origin to the star location, like this. Okay, so once we have computed this vector, the idea is to take the x and y component of this vector and divide it by the cell spacing, or the distance between two grid nodes along the x direction and along the y direction. Then we basically can count how many times we can do that. So that's like 1, 2, 3. That gives us the I index in 0 based index notation of the star location. So that would be 3. And along the y direction, 1, 2, 3. So that would be cell number 3.3. This is the cell containing the star location. If I move the star to some other place, sorry, just pick up the star. Let's move it to, say, this location. And we find this vector again from the origin to the star location. And we divide by dx and di. We'll see that we have 1, 2, 3, 4, 5. 1, 2. Sorry, only 1. And 1, 2, 3, 4. So this would be location 4.1. This is this cell in 0 based index notation. Okay, so this would be the first step. Find the index of the local cell containing the star location. Let's see how to do that in Mabel. So I'm gonna find my Mabel. It's up here. And this is a little bit of prototyping, so we will write some code while we go along. So the 0 indexed I index, I would find that by taking the x location of my star position, could call that x star, minus the origin of my grid. Here's a little detail. We need to remember what grid we're working with. So right here I'm just assuming the pressure grid, but if we were with the x component velocity field, I would need to actually subtract the displacement like this, right? So this we need to remember when we write the interpolation functions. Right now, just to sketch out the code, I'm just going to use the pressure field like this. Okay, then we need to divide by the x spacing between the cells, but I only want to know how many times this number divides up into this number. So I'm gonna take the floor of this result like this, and similar for the index along the y direction, except I'm gonna change like this. Okay, this is how I'm gonna get the indexing. If we're gonna go back and look at the grid one more time, we'll notice that there can exist some bad cases. Let's say if I moved the star to a location outside the grid, for instance, outside here, then we will notice that when we do this operation I just explained, we will compute an index value that does not exist in our data structures. This is of course a problem. When we start looking up values, we will get some funny memory errors when we do this. So the way we're gonna deal with this is basically we're gonna clamp this star position to the border of the grid, which means that if you're gonna be in a location like this, then the grid is gonna behave like the star were placed just on the border here. It's a bit difficult to move it. Which means that the containing cell would be this cell that I'm suggesting right here. And then we don't have any index errors. So the idea is basically if we are outside our world, being the grid, we're gonna project back to the closest point on the grid and use the containing cell at that location to deal with the interpolation. So let's go back to this function I have here. So there are two ways to go about this. I could basically say that I'm gonna clamp this index I compute to the maximum allowed index. So in the x direction that would be m, and in the y direction it would be n, like this. And of course along, if we were on the other side, this is when we go beyond or above the index. We could also go below, having negative indexes. That would not be nice either. So we're gonna make sure we don't have that. And we can do this like this. Okay, let's see if MATLAB likes this. Okay, seems it transformed nicely. Okay, this makes sure that we have some valid indexes. We could also actually do this on the actual coordinates. So we could say that x star were not allowed to be negative or go beyond the maximum x coordinate of the grid. So this is a bit different. So we can do it like this. So you're not allowed to have a coordinate larger than the origin of the x. So that has to be a max, like this. And the maximum x coordinate we can have would be this value. Let me see if I did that right. Yeah. Like this. So this is just meaning that we are claiming the coordinates that we're working with. And of course I need an, so let's call that input point. The input, we're gonna clamp the input to the star value, and then we can put the star value in here. If we do it like this, then we don't need the mean and max bounds on the indexing. We do similar for the y coordinate. So this could be a procedure. get cell index on P, and we're gonna have as input, we're gonna use a position. So that means that X input will be the first coordinate, that vector coming in, similar for Y, like this. Okay, I think we're almost set. And then we could create a index output. It's going to be a vector having the indexes we computed as a result. And then we need to make sure that we declare all our variables we use correctly. M, N, Ox, Oy, Dx, Di, and we need some locals too. So this would be a local, 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 local. That's just about it. Okay. Let's see if Mabel likes what I wrote. There's an error here. Let's try again. This looks much better. Okay, so this is how we can get the containing cell, or the index of the containing cell, given an arbitrary position in space, and given that it's the P grid that we want to work with. So now we could create similar versions for the X and Y component of the velocity field. So I just explained how to give the cell indexes from the velocity, from the pressure grid. And the code is pretty much the same for the velocity fields, X and Y components. I just copy pasted this function down here and here and made some adjustments. So you notice that I made adjustment on the origin of the X coordinate for the X component velocity field, and for the Y coordinates, origin coordinate on the Y component of the velocity field. I also debug the code a little bit so I catch a few typos. So you notice, for instance, that I had a P here, which is a pulse, it's coming from the argument. And I can see that I have some more small typos. Here it's gonna be the number of grid nodes along the Y direction, not X direction. Okay, I think this is it. Okay, so now we know how to find cell indices. We are not quite done yet. We need some more functions, so let's go back and design. So now we need to know what to do when we have found a containing cell. So let's go down here and make an example of that. So we have a star location like this, and we have a containing cell. Let's make it a little bit bigger so we can see what goes on. And of course we have some grid node values on this containing cell. Let's just make this something like this. Okay. Okay. And of course we just learned how to compute the I and J indices of this containing cell. Knowing the indices, we of course know how to compute the position of lower left grid node. So that would be OX plus I times DX, and the Y component OI plus J times DI. And if we want to have a location of this one, we simply just need to add a 1 to the I index, and up here a 1 to the J index, and this one would be +1 +1 to both I and J, and that way we could compute the coordinates. Now to find the value at this position right here, we're gonna interpolate the values at these grid nodes at this location. Let me label these grid node values. Let's call this V00 for instance, and the one over here we will call that V for value, 1 along X, 0 along Y. This one up here is value 1 1, and the one up here will be value 0 1. Okay. Then I want to know where this star location is located within this cell. So we're gonna compute a little local vector. Let's use this fancy one more time. From this lower left corner to the actual star location. So we already saw how to do this for the big grid. Now we just need to do this from this local cell. So we're gonna compute this one here. Then we're gonna take the X component and Y component and divide by the spacing between the grid nodes along the X direction and Y direction. We see if we do this, we get a number out. We will call the number along the X-axis for, let me just get this down here, S, and the number along the Y-axis, we will call that for T. And sorry, I don't want text here. I want a line. Let's just create one. We'll make it black. So the T value would be out here on the Y-axis, and the S value would be on the X-axis. S and T would be value between 0 and 1. So if the star input goes down and touches this line over here, we notice that S would be 0. If it goes all the way over and touches the other side, the value would be 1. And similar for the T parameter. So let's just write up here that S would be equal to, so we have the X star position minus I times dx divided by dx, and similar for the other direction. And this is of course J we're gonna use here, like this. Okay, so the idea is now we're gonna interpolate first along the bottom line from V00 to V10 using S, simply linear interpolation, to find the new value. Let me just use some other color for that. Gonna find the value at this location using linear interpolation, and similar on the top line we're gonna find this value up here using linear interpolation. When we have these two values, we're gonna interpolate those along the I direction using the T parameter, and when we do that we'll find the new interpolated value. Let me find some fancy color for it. Let's use red for instance. Oops. There we go. Interpolate the two green values along the I-axis to get the value right here. That's the idea. Okay. So let's write up how that works. Just gonna remove some of the stuff that we don't need here. This would be interpolation along here, like this. Okay, so let's name this one down here at the bottom. It's gonna be the interpolated value, and it's gonna be along the bottom line. So we're gonna do it like this. And this one we will call VS1. And the value right here, we will call that VST. Okay. So VS0 should be equal to, let's see. So if S is equal to 1, we should have the value V10. So S times V10. And if S is equal to 1, this should not contribute to anything. So that should be 1 minus S times V00. That's it. So this would be a linear interpolation of the values along the x-axis here. And the equation for the top line looks identical. The only difference is that it's gonna be the grid nodes from the top line that goes into the equation, like this. And finally, we need the T interpolation. So the equation will be somewhat similar here too, except it will be the T parameter. And it would be VS1, the top line we want to have if T is equal to 1. And we want to have the bottom line if T is equal to 0. So it will look like this. This is how we're going to find the value VST at the start location. Let me just clean up a little bit here so it looks nice. That's pretty much it. Now we need to implement this in Maple. So we'll create a procedure for it. Let's call it Interpolate. Like this. And it's gonna be in the pressure field that we're gonna work with for starters. And we want to have the 0 index of the cell, containing cell, as input. And we also want to have the S and T parameters as input, like this. And we have to recall that our data structures, they're really not using 0 indexed notation, they're using 1 indexed notation. So we basically need to start out by converting 0 based indexing to 1 based indexing. We do this like this. And similar for the J index, like that. Okay, so far so good. Then we need to extract the proper value from our grid, V00. And this is the pressure field, so it's going to be P. And it's going to be lower left corner, like this. And then we need the other corners. Along the X, along the Y, along both directions. Okay. And then we need the interpolations. And the final interpolation. and we need to return the result. Like this. And immediately just gonna remove this, and we're gonna copy it and create similar versions for the X and Y component of the velocity field. Okay, so now I've copied my pressure field interpolation to the X and Y component of the velocity field. It's pretty much the same. The only difference is it's a different grid I'm extracting values from. And we are now ready to actually combine the pieces we have into some higher level functionality. So let's just create a function. Let's call it get velocity. And it's going to be a procedure, and it's going to take in an arbitrary position as a vector. And it's going to return the velocity at that position. And first we're gonna get the indexes, or the indices, the I and J zero-based indices of the containing cell. Let me just see, what did I call that function? Get cell index U. And it took as input the position. You can just pass along the argument for that one, like this. And we need to remember this is for the U field, and we also have the V field, like this. Okay. And then we need to interpolate on the U field, and we're going to interpolate with the U indices 0, first value, and the second value. And then we need the US parameter and the UT parameters. We have not computed those yet. We need to do that in a minute. And similar, we need to do the same thing for the V field, like this. And we need the S and T parameter with respect to the V field. Let's just see, this would be the U velocity we get out from this one, and the V velocity we would get out from this one. I call those values U value and V value. So now we almost pieced everything together. You only need to compute the S and T values. So US would be equal to see if we got the number of parentheses right. One too many here. Oh, that turns out right, because we need to divide everything by dx. like this. And t, similar, set this y coordinate going in here. There's no displacement of this field. Like this. And for the y component, it's displaced along the y direction, like this. Need to take that into account. And it's of course the v indices, like this. That looks about it. And we of course need to create locals for these parameters as well. US, UT, PS, VT, and we also need to declare the globals we're using. So we're gonna use dx, dy, ox, oy. This should be sufficient. Let's see if Mabel likes it. Mabel does not like it. Oh, we forgot to make locals for the u indices and v indices. Like this. That looks better. So that's it. That's how we're going to find the velocity at any given position. We now have the basic functionalities of our data structures in place, and we can start talk a little bit about the numerics for actually solving the Navier-Stokes equation. So we will do that in a little minute.